Greetings, Earth enthusiasts. If you ever wondered about the incredible perspectives our planet has to offer from high above, you're in the right place. I am Dr. Clive Coetzee, and I'm thrilled to be your guide on this captivating journey into the world of remote sensing. Welcome. And please remember to like, subscribe to, and share this video. Thank you.
Alrighty then, so in 120 we continued where we left off with 119, tutorial 120, 119. They are pairs, so you need to look them as pairs. So it's all about spatial regression, applying spatial regression models or modeling to my region of interest, specifically to model NDVI in my region of interest. And we've been doing this for the last number of video tutorials. So remember the equation stays the same. NDVI is equal to elevation, rain and temperature. Now whether that's a good equation or not, that's debatable, but it's for illustrative purposes that we're working with that equation and we're applying different methodologies to it to see for this particular region of interest, for this particular dependent variable, which of those methodologies yields a superior results, modeling results for prediction. We want to predict the values based on those three explanatory variables. Okay, so we finished in 120 with our 7 spatial regression models. We generated those models, we estimated the predicted or the fitted values, we rasterized them within RStudio, and we then imported into QGIS, and then we compared them. Remember the last two we had to do a bit of interpolation because we can't do prediction, or if we can't do the predicted values and rasterize them, we had to work with the fitted values. Okay, so that's all in 120. So in this particular video tutorial, we're going to focus on a class of regression which are called sorry, let me just quickly go there, which are called geographically weighted regression. So that's a methodology, a regression methodology that assumes non-stationarity in the variables, which are it's always important, and also look at the location of it. It's not spatially per se, but it does include the neighbors, and use different methods to include the neighbors. So it's something similar to the spatial regressions that we did last time, in that it does include a spatial component, but it does it in its own unique, and it doesn't look. It looks at the geography of the area, not specific locations per se. So that's sort of where the difference lies. So it looks at the area as a whole and not individual locations. And that's what the geography part comes from. It's not spatial in terms of the elements itself. It's the whole region of interest. And then as it's a major thing, it does not assume stationarity in the variables. So that's the major thing. So it is time series, but expanded to include my region, the spatial nature of my region of interest, and not just individual locations. So, okay, so it's somewhere between spatial econometrics and time series econometrics, sort of lies in between. There's two sites which I can strongly recommend, which is this site by Professor Noli Brazil. That's quite a good site to work with geographically weighted regression. There's another site by Roger Bivant, which is also worthwhile, and then there's this site, Introduction Geographically Weighted Regression. It's a bit outdated and a bit short. It's not as good as the other two. I would definitely look at Professor Brazil and with Roger Bivant. Those are the two sites that I would recommend. Okay, so using the information on those two sites, I've built my geographically weighted regression modeling, and I said the idea is to generate rasterized predicted values and then compare how this set of predicted, or this set of regression methodology compared to the others. Okay, so we would then have 4 sets of regression methodology or prediction methodology. We would have the the random forest. Okay, so that's a set of regression methodology. We will have time series, which is multiple regression. We'll have spatial regression, and then now we have weighted regression, geographical weighted regression. So that's 4. We're still going to do that vector matrix, support vector matrix. So that's 5. So we're going to look at 5 of them, and obviously within each 5 there's a whole lot of methods, slight variations, etc., etc. So, but the 5 methodologies in principle is going to be that 5: random forest, time series, spatial, geographically weighted, and support vector. That's the 5, and then we're going to evaluate all of them and see where we come. Anyway, so where do we start? Okay, so we are in our I keep on saying Earth Engine. So you used to say Earth Engine. We're in RStudio. Okay. First thing that we have to do is we have to create a spatial. It requires a spatial data frame. Okay, it requires a spatial data frame, and specifically, it requires. Where are we now? Class. It specifically requires a. Where is it now? It's called a. Now, for the life of me, can't remember what the hell the thing is called. Here we go. Yeah. It's called. No, almost there. I just ran it now. For the life of me, I can't remember what it's called now. A spatial points data frame. That's what it's called. Sorry about that. It's late in the afternoon. It's called a spatial points data frame. That's what you need the data set to be in. It needs to be in that format. Otherwise, it's not going to work. Okay. So remember, it needs to be in a spatial points data frame format, and then it can work. So there's my numbers. Okay. Let's go back. Okay. So we have our NDVI, which is our standard CSV file. Okay, so it's that standard one. We then bind it with its X and Y coordinate. Okay, so it's our standard CSV file with our standard data. Okay, we then bring in the coordinates and we bind the coordinates to our data, and we set it as a spatial. We convert it into a SF file. Okay, we convert it into a SF file. Okay, so that's important. So that now implies that it's a spatial points data frame. Okay, so that implies it's a spatial points data frame. Okay, then I convert this into. So remember, this is a CSV file. I'm converted then into a shape file. Okay, so you see there it is. Okay. See, I've loaded that's a spatial points data frame. This one here, which is my normal CSV file that I've transformed in a spatial points data frame, and then I save this spatial points data frame as a shape file, a normal shape file. Okay, there it is, and I call it NDVI NDVI4. Okay, I call it NDVI. Then I open the NDVI form. Shape file, this one here, meaning this spatial points data frame. Basically, in a shape file, I open it, I read it as a S3 because we saved it as an we created a SV for them, and then we just assign it that it's spatial, etc. So we need these steps. Okay, we need the steps to create the format for the geographically weighted regression, i.e. it needs to be in a spatial points data frame, and that's how we create that. CSV, bring in the coordinates, save it as a SV, write it as a shape file, open it as a shape file, and assign to it the term spatial. And there it is, NDVI w.sp. Okay, the W is just for whatever, I can't remember why I call it W. I just have no idea why I call it W. I should have called it SF. And then for the SF, we convert it into a SP. Okay, so we convert the SF into a SP by using the as spatial. Okay, so now we've created a if I do that, let's quickly just do that. I'm not going to do the glimpse. I'm just going to see if I can run that. Yeah, it's now a spatial points data frame in the SP format. Okay. So from SP, using the spatial, I create the SP, and now it's a spatial data frame. There's the values and the minimum and maximum values for each of values. There's the variables and the minimum and maximum variables. There is the X and Y coordinates. Features 5259, variable 6. So there it is. So now I've created my spatial points data frame. Once I've done my spatial points data frame, I can now start with my modeling. And in essence, within the geographically weighted regression, I'm going to run 3 models. One uses the Gaussian function to determine the bandwidth. Second one, use the bi-square function to determine the bandwidth. And the third one, I'm going to use an adaptive kernel. So that essentially, there's more that you can do, but these are the 3 main geographically weighted regression models. Okay, so the first what we need to do is we need to calculate that geographically weighted function, which is called the bandwidth, and that's done by this particular format, GVR, geographically weighted regression dot cell. Okay, that creates the bandwidth. Okay, that creates the bandwidth. You see there's in same one there, same one there. So that's standard format. That creates the bandwidth. Now the bandwidth, this one here that we create, is basically a weighted method. Okay, that we then use within our modeling. You'll see there our bandwidth that we've created there, NDVI BWBI. You'll see there with our bandwidth, we link that. You see there, we link that. Okay, sorry, there it is. We link it, the bandwidth. So we have to generate the bandwidth. We have to generate the bandwidth before we can generate the equation itself. Okay, so the bandwidth, I've already run this. Again, I'm not going to run the model again because it takes 2, 3, 4 hours each time. So I'm just going to run the outcomes. I'm not even going to do that because that's going to take a whole lot of time. Just to show you, this is sort of what we get to. Where is it now? Where did it run it? There we go. It creates a bandwidth. Okay, so you see there, cell NDVI alerted this. There it sits. It's this one here. And if I run it, I get the bandwidth. Okay, there's the bandwidth and the scores. Again, if you want to find out what all these things mean, please consult that documents. Now, I've generated the bandwidth. You can see these numbers here. And within this band, now I'm going to generate my geographically weighted regression by using this particular bandwidth. And remember, in this bandwidth, the default function to create those bandwidth, or the weighting function, is the Gaussian function. Okay, it's not specified, it's by default. And that's how it looks like. Now, again, if you just, that GVR is a standard geographically weighted, there's my equation. The data is that SP data set, the spatial points data frame. That's the data set, okay? This one there that I've created. That's my data set. The bandwidth is the one that I've just created here. And then we have 50, which is basically create the standard errors. Standard errors. So to create the standard errors, and this hat matrix true is calculating a whole lot of statistics with it to determine the coefficients, accuracy, and all sorts of things. So it's just creating a matrix of information related to this. We don't have to do these 2 things, okay? That's optional. But if you want to generate the t-statistics and all these things, you want to generate the standard errors, and you want to generate the coefficients and all these things, you want to do this. Okay, so this is just to tell it to go the full Monty, so to speak. Generate all the information relevant to this specific model. But the important part is the data that you're going to use, that it will be in the spatial points data frame format, and the bandwidth that you've just created using the Gaussian function. If I run this, this is the result that you get. It says there the kernel function is a Gaussian. It's got a bandwidth of 0.07 that it used in this case. The bandwidth that it used, there is the coefficients, but you see now it doesn't calculate one coefficient per se. It calculates a range of coefficients. Okay, so it will calculate a minimum for first quartile, median, second quartile, and a maximum for each of these variables. So for elevation, the minimum coefficient is -2. The first quartile coefficient is -3. The median coefficient is -3.5. The max third quartile coefficient is 3. And the maximum coefficient is, elevation coefficient is 2. So it calculates 1, 2, 3, 4, 5 coefficients for each variable. So it creates average coefficients for all of my locations. Okay, and then it presents those in those statistics. Okay, so it doesn't create one coefficient for all of it, for all of the locations. It creates coefficients for each and every single location. Okay, so that's important to understand. So that's what. So which coefficient to use? The system will determine that. The program will determine which coefficient, but you can use the median coefficient, for example, or you can use the first. It's up to you. I would suggest the median coefficient. The median coefficient. Okay, that's why we've created this hat matrix T, is to generate all this information which we can use. Okay, so I've got this now. Okay, so now I'm going to use my standard methodology, standard method to generate, to rasterize my predicted values. So I've got my model, I've got my coefficients that is generated, of my range of coefficients that it is generated. It uses the median or some coefficient that it automatically generates, and now using that we're going to generate the predicted values. Okay, we're going to get the predicted values. Let's see if I go and say fitted. Let me see if I do that, whether it will present the fitted values. Let's quickly do that and see if it works. It should work. No, it doesn't work. So it doesn't operate, it doesn't want to do that. Okay. So I'm going to do now the predicted values. It's a little bit different in that it is the model, and then this SDF standard thing. Not sure exactly what its purpose is, SDF, but it's there, and then it says predict. So that is the notation or the script to generate the predicted values. Okay, so I'm going to just run that. Now it has created the predicted values. So if I go predict NDVI WR, let's say NDV predict, see if we can find it. Nope. Values NDVR predict, there it is it NDVI WR, there it sits. Okay, there it's loaded. There's my first value, 0.453, second value, fourth value, etc. So it's already loaded there, 5259 of them. It's loaded there. Okay, so the next step again is exactly the same. We go now into our template. So we take these predicted values and we assign the coordinates, and we get the coordinates from our normal NDVI. We get the coordinates. Okay, so we get the values, our predicted values, and we bind it with our coordinates, and we create a data frame. Okay, so that's done. Then we take that and we superimpose it on our empty raster. Remember our empty raster, the one that we did in spatial, exactly the same raster, which is an empty raster but with the extent, coordinates, etc. as the original raster. Then we can plot it. And we can save it. I'm not going to save it, I've already saved it. So this part from here onwards is exactly the same as we did with the spatial econometrics, the spatial regression, where we rasterize the predicted values. The only difference with geographically weighted regression is this part in creating the predicted values. Okay, this is where it's different. But the rest are exactly the same. We bind or we bind or we assign with those predicted values the coordinates. Then we superimpose it or we add it to our empty raster, our template. Okay, and then we basically just plot it and export it. As simple as that. Nothing to it. Okay, so we'll have a look at it now in QGIS. Then remember we did a second one, which just used the by square as our weighted function. So you'll see there, gweight is just called by square. Okay, so that's the only difference. You'll see in the original one we didn't include it because we could basically say weight is that Gaussian, but it's by default. So now we just include it. So now it's just a different method of creating the bandwidth. We've created the bandwidth. I'm not going to run it, and then we include. I'm not going to. It's going to take a long time. We take this bandwidth and we include it in the model itself. You'll see it's exactly the same as the original model. There's the original model, except that we now also just specify it is using that. It is the bandwidth that we just created there, PI, and we just specify it as well. And the rest is arrows, hat matrix is exactly the same. And let's say if we run that, there it is. Again, minimum, first, medium, third quartile, and maximum. Exactly the same. Now we rasterize the predicted values, same as we did before. Just gonna, okay, so it's from that to this point here. We're gonna run it, and we're then gonna plot it. Okay, there it is, and we save it. I'm not gonna save it, I've already saved it. So that's the second geographically weighted regression that we've done. One with the Gaussian function to generate the weights and the bandwidth. Second one, the bi-square function to generate the bandwidth and weights. And the third one is we're going to generate an adaptive. We're going to use the adaptive kernel to generate the bandwidth and the weighting. In this, to generate the bandwidth, we just use adapt is equal to true. Okay, so we don't specify the weights. We just the function. We just use adapt is equal to true, meaning use an adaptive kernel. We run that. We add that now into our model itself. We run that and see how that looks. And there it is. Again, minimum, first quartile, median, third quartile, maximum. And we do the same. We create the predicted values and we rasterize it. Let me just quickly do that again. We're going to run that. And then we're going to plot it. Okay, and we're gonna write generate write the raster file. So let's quickly see if we can put them next to one another to see how they look so we're gonna say it's 3, so we put them next to one another. It's at 1 to 3, 1 to 3, I think. 1 column, 3 rows. Now we're just going to get them plot that one there. We're going to plot that one. Then we're going to plot that one. And then we're going to plot the third one. So there's our three models. And let's quickly run them. Let's just close. Sometimes you have to clean that. Okay, so let's see if it works now. There we go. It's not that great. Let's zoom. There is the 3 of them. Looks very similar. From obviously it's very small, these ones, so it will be difficult to see changes, to see if there's changes between the three of them, or the marginal changes. Anyway, let's keep it there, save it. Let me just quickly up this, because that leads into a spatial regression that we're doing. So that's the three, save it, our three geographically weighted regression models. Okay, it starts with creating the necessary data frame, the spatial points data frame. Once you've got that, then you can run it. Okay, so I've now then exported it into our QGIS using our normal, and there they sit. So let's go. There is our first one, the Gaussian method. That's our bi-square method, and that's our kernel method. Okay, so there's all three of them. Doesn't look too bad. So let's see how they compare. So I'm not going to compare them to all of them. We'll do that at a separate stage, but just to quickly say, there's the actual, and then we select the three geographically weighted models. Let me do that one. There's the three of them with the actual. Let's go and let's look at a specific location. And there, the three of them, let's first look at what the actual value of the NDVI is. The actual value is 26. Let's see the first one, the Gaussian model, 0.3. The bi-square model, come on, 0.38. This is 0.300. This is 0.38. And then the kernel, which is 0.31. So it's a little bit off. Let's try a different point. Let's try one there. See if we can generate the differences now. That's the actual, yeah, 0.48, 0.42, 0.53, and 0.53. So the first one, the Gaussian one, seems to be the more relevant, and we can play around with this. Okay, so that is the geographically weighted regression. Doing that in R. Remember, this is combining again time series with spatial nature of my region of interest, but not the individual locations per se. There is a difference. Okay, it's specifically how you calculate the relationships between the neighbors. That's really where the key lies. And as I said, we run them, and then we generate the predicted values, and we rasterize those predicted values, and we ship it into QGIS, and voila, Bob's your uncle. Okay, so as I said, good stuff. So that's on the geographically weighted regression. I still have to complete these time series models. I'll do that soon. Well, so 1, 2, 3, 4. We've done the first two, which is the robust linear square and the which one? There was one more that we did. I can't remember. This one here, the LMS one. So those two that we've already done. We still have to do these three, so I'll do them. So I'm not going to do a video tutorial on them. I'm just going to do them and include it. And then we then have to do the support vector machine modeling to see what that looks like. Okay, so that's going to be a separate video. It's a support vector machine, and once we've done that video, then we have all our rasterized predicted images within QGIS, and then we're going to compare them and see what we get. And then I still have to do a video on Geoda in terms of creating the weights. So those are all in a pipeline. That's upcoming, forthcoming attraction, so to speak. Yeah, so thank you very much for joining me. I really appreciate your dedication and support to my channel and to what I do. I really appreciate it. Please remember to like, subscribe, share the video. Yeah, please subscribe. If everybody that watches subscribe, I would reach my targets within no time. So please, please, please subscribe. I really count on it. Thanks again for joining me on this journey of remote sensing, and I'll see you on the other side.